So in the previous video, basically the Navier-Stokes equation was constructed from the oil. So basically the idea is if there was a blob moving in space, or a blob of fluid moving through other fluid, and the fluid moves faster or slower past that blob, it actually causes a drag force on the blob. It's kind of a skin drag due to the differences in velocity of the flows, and the viscosity tends to try to equalize that velocity. So this video will basically cover the physical interpretations of the Navier-Stokes. So this is the Navier-Stokes right here. So the significant part of this is actually just the Euler equation. So this and that, basically, this part basically just comes from the Euler. And that has already been discussed. So the part that's actually of interest is this part right here. So the question is, what all does this mean? So what this set of constants and then times basically this divergence of the kind of the gradient of this vector field. So what is this? So to start with, it just will go through what the equation actually is. So what the symbolism actually means is actually the Laplacian of each component. So we have this divergence of what's kind of like a gradient of u. This thing actually written out looks like this, which is the divergence of the gradient of ux, divergence the gradient of uy, and the divergence of the gradient of uz. So it's actually just the Laplacian of each of these components of u. So writing this out further for each component, basically have, for example, we'll take the x component again. So it's basically the Laplacian ux. And what this actually equals is the second derivatives of everything. X squared plus t squared ux ty squared plus t squared ux and the dz squared. So it's basically this that contributes to the change in the ux per change in time. So what actually contributes to ux, so delta squared ux, which is another way of writing this. This is just this thing, delta squared ux, is what to basically the change in the velocity field will change in time. So basically going back to the equation, so each of these, this du dt T basically has a ux, uy, and uz, and each of these correspond to one of these guys. So the change in the x component of the velocity with respect to time has a contribution due to the Laplacian of the ux, and then the same idea, the change in the y component with respect to time has a contribution due to the Laplacian of uy. So basically what's affecting the force of viscosity looks like the Laplacian of the component of the velocity, and that creates a force in that component's direction for each of, in this case, the three components of the viscosity, or the three components of the force. So the question is, will this viscosity actually exist in the fluid? So to start with, we're going to look at what a second derivative actually is. So basically what's going to happen is the viscosity term, the force from the viscosity, is going to get stronger anywhere these second derivatives of the velocity component exist. So this is just to get the idea what a second derivative looks like. This is a general function which is kind of arcs upwards and downwards. It's actually I think it's called a third degree polynomial. The highest term is the x to the power 3. So this is the function, and then the x-axis is. So taking the first derivative of this, the first derivative is basically the slope of the line. So the slope down here is positive, and then it decreases until it's 0. So we have positive slope decreasing to 0, and then the slope goes ahead and turns over and starts going negative. So we have negative slope through there. Slope reaches 0 again there. That's why the df dx is at 0, and then it starts increasing again. So this is the graph of the original function, and then this is the graph of the first derivative. Then going on to the second derivative. Second derivative basically looks like this. It's just a straight line. So basically the slope of the first derivative was basically negative, and it keeps going negative but decreases, so it's less negative until the slope is 0 right there, and then it increases to being more and more positive. So it goes across, and it just has a straight line that crosses over. So for viscosity, viscosity depends on all of these second derivatives. So basically what it's looking for is a kind of curvature in the velocity is what's going to lead to a viscosity term. So start looking at some cases. So first case. Case. Let's try ux equals 0. Then, so obviously, radian square root of ux is going to equal 0. So that's kind of a trivial case. This also is true if ux is constant. Ux equals a constant. Then the gradient of course has a derivative in it, and the derivative of a constant is 0. So basically the thing is just moving along. You have the blob moving along, but everything's moving at a constant velocity. There's no change in relative position, so there's obviously no viscosity. Because if everything's moving at the same thing as a solid block, it doesn't lead to any viscous force. So the next case, and this is a little more interesting. So here was the second case. In the second case, ux is not a constant, but the derivative of ux is a constant. For instance, dux dy equals a constant. So what does this look like? So I'm going to draw this out here. There's the blob. There's fluid moving there, and then it decreases. It's like a linear decrease. Like that's supposed to be like a straight line. So the velocity just keeps decreasing. Now it turns out that dux dy squared is still 0. So the question is why? So to look at this, need to look at this in a little more detail. So basically take this blob. So there's a difference between the two forces on top, and that does indeed lead to a force going in this direction that's trying to drag it along. There's also a difference in the two forces on the bottom, but it turns out since the blob's moving faster than the fluid outside, that force is actually going in the other direction. And what it turns out is when this is constant, these forces are going to balance. So I'm going to do F top and F bottom, and basically F top plus F bottom is going to equal 0 because F top equals the negative of F bottom. So what this basically corresponds to is where the forces, there's a force on the top and the force on the bottom, but all that's happening at the skin is it's just spinning around in a circle. So this does not actually lead to a net viscous force. So in order to get a net viscous force, there actually has to be a kind of curvature in the velocity. So ux, let's say, suppose ux is curving in magnitude. Along y. So basically I have this case again. And there's basically a ux up here. Let's suppose the ux down here is actually smaller. And then this ux is bigger again, not as big. So this thing kind of has a curvature. It could be called as kind of a curvature to it, in the sense that ux was plotted as a function of y. You can see there's kind of a curvature to this in the velocity. So what happens here is it actually does have a real viscous force. So for this dux squared x squared, the magnitude is going to be greater than 0. So there is actually a force of viscosity here. So to see why that happens, so we draw this thing again. So there's basically going to be a force on top that's going to go forward. And then because this thing is actually dragging faster, this is going faster than the fluid inside the blob, there's actually another force on the bottom. And the forces actually point in the same direction. So this is force top, this is force bottom. So the magnitude of force top plus force bottom is going to be greater than 0. Because these guys are both, in this case, they're both pointing in the same direction. So this is the case where there's actual viscosity. And this can be shown similarly for the components that go along that are kind of the stretch components. So for the, okay, similar. Logic can be used for this case where you actually have a viscosity where there's actually a kind of a stretching difference. Which is to show that Ux is greater than 0 for certain types if there's kind of a magnitude change in the Ux. So in that case, let's go ahead and graph Ux. So if you have a case, it was the x-axis, Ux. So just so long as there's actual curvature in the Ux, there's going to be a non-zero du dx. For the pulling also. So to look at this in from the program, I also have a number of these images. So this is basically after the sliding wall. So the sliding wall has effectively generated this rotational field in velocity. And you can see how the velocity is moving at different, as well as there's the higher velocity closer to the sliding wall and lower velocity up towards the center of the vortex. And this color scheme on the background is the intensity of the viscous force. So there's more viscosity here, there's actually almost no viscosity there, and there's a lot of viscosity around here. And the reason why there's almost no viscosity is because it's basically a linear decrease. So each of these is decreasing, but they're decreasing in a linear fashion. So having a dux dy that's non-zero does not guarantee that there's viscosity if the decrease is almost constant. And so the next slide is the viscous force. So you see there's almost no viscosity here. And then these are the directions of the actual viscosities. And the error magnitude is accurate in a relative sense, but it doesn't have any significance as its absolute value. The arrows were just set to a size that made them visible. So there's a lot of viscosity up here, practically none there. And the viscosity is going actually in the opposite direction to the rotation. So this was the rotation going around in this direction, the actual velocities, and then viscosity is actually opposing that. Here's another slide. This is after this vortex has been spinning around detached for a while. There's no longer a sliding wall. So it has these velocities as it spins around its center. And the color scheme is again the magnitude of basically the magnitude of the viscous force. So there's more viscosity up here, and then there's this layer where there's almost no viscous force. And then over here, even though there's not a lot of velocity, there's actually a fair amount of force from the viscosity. So going to the next slide, we'll show the actual directions of the viscosity. As can be seen here, and viscosity again is basically opposing the direction of motion. So the viscous force is going around basically clockwise, whereas the rotation was actually counterclockwise. So that's this viscous force, and then yet one more slide. This again, these are these little vortexes. I changed the color of the background that indicates the intensity of the viscous force. But again, the color scheme on the background indicates the intensity, and the arrows indicate the flow field, the direction that the fluid is actually flowing. And so there's these two little vortexes where the fluid comes down the middle and then rotates in opposite, kind of counter-rotates off for both sides. And the next slide will show the direction of the viscous force. And see that the direction of the viscous force is most intense in the center, and it directly opposes the motion. So the fluid motion is basically going down in this top vortex group, dual vortex. So the velocity is basically going down through the center, but the viscous force is going in the exact opposite direction. And that basically kills off these vortexes. That's why the vortex down to the lower left actually has very little energy in it. It's because the viscous force has actually drained it out so quickly. That's basically dying out. And of course, viscosity is most intense where the Laplacian is the most intense. And it can kind of be seen here because the velocity in the center is the greatest, and then the velocities on the two sides are smaller. In the center of the top right vortex, it's kind of obvious how that actually generates the second derivative of the Laplacian. Okay, so the next we'll go into the numeric solution.